Hello, hello. Welcome back to Short Takes 331. Today, we're going to continue talking about linear systems of equations. So this is our part two. And let me remind you then that a linear system of equations is something that looks like this. So here is a system of m equations with n unknowns. And we have our coefficients a11, a12, all the way through a1n for the first equation. We have our right-hand side b1, and so on for every equation. And so we have a collection of m by n coefficients, and we have n unknowns, and we have m right-hand sides. And using matrices and vectors, we saw last time in part one that we can rewrite this whole system, this big mess, in a very simple and compact way as a times x is equal to b, where this a times x is a matrix product vector. And our job here is to solve for x. Now, very generally, what I mentioned last time is that if you have more equations than unknowns, typically there will be no solution. And I will say very briefly in a few minutes what we mean by typically. Okay, but typically, if you have more constraints than unknowns, you will not have a solution to your problem. If m is equal to n, if you have as many equations as unknowns, then you may have a unique solution. It's possible to have a unique solution. So not only would there be a solution, but it will be unique as well. And if m is less than n, you will have fewer equations than unknowns. And so typically what will happen in that situation is that you will have infinitely many solutions. Now, in all these cases, that would typically will happen, but there's some caveats that we have to address where these things may be a little different. And those caveats go by the name of degeneracy and consistency. So degeneracy is something that will happen, and that we saw last time in part one, where equations contain superfluous information. So you may have a situation like this, for example, where you have two equations, and the two equations read x1 plus 2x2 equals 9, but then the second equation looks like this, minus 2x1 minus 4x2 equals minus 18. This second equation clearly is just multiplying the previous equation by minus 2 on both sides, and so it doesn't really tell you anything new. They're linearly dependent. And so that could happen for you in any of these situations. You could have a situation where m is greater than n, and it may look like there's no solution, but in reality, you may have many equations that are superfluous, and so you may actually be, once you remove those extra equations, you may be in m equals to n case, and so you have to account for that. Similarly, in this m equals to n case, you may have some extra equations that don't really tell you anything new, and so in reality, you're looking at an m less than n once you remove all those extra equations, and you may be in a situation where you actually have infinitely many solutions. So you have to be mindful for that, and there are ways to do that, and we will learn about those in upcoming videos. Now, the other issue, the issue of consistency, is also very important in that you may have equations that contain inconsistent information. So you may have a situation where you have your first equation that looks like this, 2x1 plus 3x2 equals to minus 1, but then the next equation is minus 2x1 minus 3x2 equals to 7. Okay, so this is clearly the left-hand side is the previous one multiplied by minus 1, but then on the right-hand side we have a 7 instead of a 1. Okay, and so this is the problem. If you sum those two equations, then you get 0 equals to 6. Okay, so the left-hand side will give you 0, and the right-hand side will give you 7 plus minus 1 will give you 6 total. And so this is ridiculous. Of course, 0 equals 6 is not sensible. This is completely inconsistent information. So one of these equations needs to be thrown out. Yeah, and so in the following, we're going to assume that these inconsistencies are not present in our problem. Now, of course, you have to be mindful that here, if the right-hand side, instead of being minus 1 and 7, were 0 and 0, then there will be no problem. Then the solution, we always have a solution x1 equals to 0, x2 equals to 0, because it will be a homogeneous problem. And like we saw last time, homogeneous systems always have a solution where all the unknowns are equal to 0. But these two then are the caveats to keep in mind when you have these systems of equations. So even in this case where you have fewer equations than unknowns, you may say, oh well, then I will probably have infinitely many solutions. You may still be given equations that are inconsistent with one another, and so there will be actually no solution. So it's something to keep in mind. But this is typically what will happen. If you have more equations than unknowns, there will be no solution. If you have as many equations as unknowns, you may very well have a unique solution. In most cases, you will have a unique solution, and if not, usually we have an infinite number of solutions, typically, and because you may have superfluous information, and then you really have the typical case of m less than n. And if you're given right off the bat this m less than n, then usually you will have an infinite number of solutions. Now, in all these cases, solving the problem amounts to putting this this matrix A on the other side of the equation. And by that I mean the operation like this. So if our problem can be written as ax equals b, then we can multiply by a to the minus 1 on both sides of the equation. So we multiply by a inverse if it exists on both sides of the equation. And so you have a inverse a, which is the identity, and a inverse b on the other side. And so that tells us that x is simply a inverse times b. And so if somebody gives you a inverse, and that is a inverse exists, then all these operations are allowed, and the solution vector exists and is unique. So if you find these videos helpful, please like and subscribe. If you need a tutor in physics and math, and you need that maybe in English or maybe in Spanish, I can help you. As long as you're not a UNC student, I'm happy to help you. And you can reach me at shorttakes331@gmail.com, or you can just leave a comment in the comment section below, and I'll get back to you. So how do we know when this A inverse exists? How do we know when there's a solution and it's unique? This is usually what we want to find out. We want to solve a physical problem and we want to arrive at its unique solution. So how do we know that? If we don't know if it exists, can we try to construct it and see if we can arrive at a solution? Or maybe even better, can we find a way to find x directly without going through finding the inverse of A? So there are ways to do all these things, and we'll see those in upcoming videos. And today we're going to take a few steps in that direction. But it's important to note that knowing this A inverse allows us to solve for x for any given b. So knowing the inverse is actually a lot of information. No matter what b is thrown at you, you multiply A inverse by b and you get the x that you want. On the other hand, if you can find x directly for a particular b that you might be interested in, then that's a lot less information and it's a lot more direct to determine usually. And so we'll see algorithms for those things as well. So, but first let's gain some intuition as to these inverse matrices. So the simplest case, most trivial case to work with is of course where A is just the identity matrix. So if A is the identity, then A times x is just your original vector x. So when we multiply A by x, this matrix by a vector x will just give you the same vector back. And so the solution to ax equals b is just that x1 is b1, x2 is b2, all the way down to xn equals bn. That's trivial. There's nothing there. If it seems very simple, it's because it is simple. There's nothing else. And here I've assumed that we have n equations and n unknowns, and there's nothing to it. Okay, it's extremely simple, just to make sure that we understand the mechanics of it. Now the next case, where we may have a chance to solve the problem directly, is where A is a diagonal matrix. So suppose that A is a diagonal matrix like this, and so when we multiply A by x, we get this vector. A multiplied by x is d1 x1, d2 x2, all the way down to dn xn. And if that is to be equal to b1 through bn, that's our equation ax equals b, then it must be that d1 x1 is b1, d2 x2 is b2, and so on, which tells us what x is. So x1 must be b1 divided by d1, x2 is b2 divided by d2, and so on and so forth. Now, in order to do these operations, we must have that all the decays are non-zero. We must have the decays that are non-zero. So all these decays have to be non-zero for us to be able to do this. Otherwise, we'll run into trouble. What kind of trouble do we expect? Well, suppose that there's some decay that is equal to 0. Okay, so if some decay is equal, suppose that d2 is 0, then this automatically will be 0. The second line will be automatically 0. And so two different things could happen. If b2 is also 0, then we can put x2 to anything we want and we'll be safe, because then both sides will be 0 for any x2. And that will give us then an infinite number of solutions. How so? Well, because x2 can be anything. And so you can fix x1 in this way, you can fix all the other x's with the corresponding equations, but x2 could be arbitrary because you multiply by d2 and you get 0 automatically, which is correct if b2 is 0. Now, if b2 is non-zero, then there will be a contradiction. We will be in trouble because we will have a left-hand side that is 0 and the right-hand side that is non-zero, and so we will have a contradiction. And so you see that if one of the decays is 0, then we run into all sorts of trouble. So for this to work out, really, we must have that decay is non-zero. And in that case, then the inverse of the matrix we know exists. It's given by the inverse of all these values. Here, A inverse is the same matrix. Basically, all these coefficients are inverted. So d1 inverse, d2 inverse, and so on. and then that solves the problem when we apply that operator, when we apply that matrix to that this vector b1 through bn. I call this an operator. We will see in a future video a more general topic of linear operators, of which matrices are a particular type or a particular representation. We'll get to that. But for now, let's look at another case. So this case 3 is where things start to get really more interesting. So far things were a little bit trivial. So suppose that A were upper triangular. Remember, upper triangular is such that the diagonal may be non-zero and the upper triangle may be non-zero, but below that everything is zero. So we have a bunch of non-zeros here, and below that everything is non-zero. That's what we call upper triangular. B is our usual B. And so what is A times X? Well, if you multiply A by X, you get this type of structure. This is a vector, by the way. So I wrote it in this big expanded way so I could fit all the terms, but this is a vector. And the first element of that vector is this whole sum, a11 x1 plus a22 x2 and so on all the way to the end. And if I do this this whole operation, I get to the last one, and the last one is simply a(n)(n) multiplied by xn. Now, this whole sum has to be equal to b1, this whole sum has to be equal to b2, and so on and so forth, because that is what ax equal to b means. And so the way to solve this problem is that you take the easiest equation first. You go to the last equation and you say, this must be then that xn is bn divided by a(n)(n), and that's what I wrote here. Now for this to work, it has to be that a(n)(n) is non-zero. Otherwise we run into the same problem that we discussed before, that we may have an infinite number of solutions or no solution at all, so we have to be careful, we have to be mindful of that. But assuming that a(n)(n) is non-zero, then we are allowed to solve this first problem like this. What happens next? Then we go to the previous equation higher up that I didn't write here, but looks like this. a(n minus 1, n minus 1 times xn minus 1 plus a(n minus 1, n times xn is equal to bn minus 1. So it's the previous equation, the one before last that I didn't write here. And in this equation we have two unknowns, xn minus 1 and xn. But hold on a second, we already know xn from the previous equation. And so what we do is we use this equation to solve for xn minus 1. So we put this on the other side of the equation. We divide everything by a(n minus 1 and minus 1, and so we solve for this guy. Again, we know this guy from the previous equation. This is known, it's given to us, and from here we divide by a(n minus 1 and minus 1, and so we put everything on the other side of the equation and we solve for that. Now for that to happen, notice what I just said, we have to divide by this. And so we will need that to be non-zero. Otherwise, what happens, again, we run into this issue of degeneracy or inconsistency, and we may have an infinite number of solutions or no solution at all, and so we have to be careful. And so you can see what happens, right? If a(n minus 1, n minus 1 is 0, then this is 0, it doesn't appear there, and now we have another equation for xn, but xn is already determined by the previous equation, so we're going to be in trouble there. So depending on what this guy is, if this guy is also 0, then maybe there's hope if this is 0, but maybe it isn't. So then you see we have to be careful. So what will save us always is if we have that a(n minus 1 and minus 1 is non-zero. Then we can divide by this guy here and we can move forward. The next equation over, the one prior to that, in our vector here, then the second from the last one, will involve xn minus 2, xn minus 1, and xn. But we already know this last two, because we just solved for them. We solved for xn, we solved for xn minus 1, and so now in this equation we solve for xn minus 2. And this is what we call back substitution. So we start with the last equation and we work our way upwards all the way to the top. This last equation that we just discussed will require n minus 2, n minus 2 will be not equal to 0 for the same reasons that we discussed before, and we continue in this fashion and solve for all the xk. And when we'll end up requiring that akk is not equal to 0 for all k's, and we must have then non-zero diagonal elements. So all this works out, and we can solve our problem ax equal to b for a triangular system as long as all this diagonal is non-zero. If all this diagonal is made out of non-zeros, then we're safe and we can solve our problem. So lower triangular systems are solved in the same way, but instead of starting from the bottom, you start from the top. So if we go back and look at this equation, then all the non-zeros will be in the lower part, and the first equation is going to be the easy one. And so we start with that one, and then you plug the results into the next one, and you work your way all the way to the bottom. And so if somebody hands you a system of equations that is not trivial like this one, and it's not diagonal already like this one, there's nothing interesting happening because all the equations are decoupled, but the equations are coupled in this way, where you have this type of structure for your equations, then you know how to solve it. You either start from the bottom, or if it's lower triangular, you start from the top and you know how to solve it. And this is one of the crucial examples that really is able to bridge between not knowing what to do and for a generic problem and actually coming up with a full algorithm to solve pretty much an arbitrary problem. And what's behind this idea that I'm saying now is that it is always possible, with some conditions, not always, but with some conditions, it's possible to turn a system of equations into an upper triangular system or lower triangular system by doing some operations on that. And once you're in this upper or lower triangular form, then you're ready to go. Then you can solve the problem in this way that I just described. So if it's upper triangular, then you can solve it like we described. If it's lower triangular, you start from the top and you do what's called forward substitution instead of back substitution. That's all I have for you for today. I hope this made sense. If you find this useful, if you're enjoying these videos, please consider liking and subscribing. And as always, if you are looking for a tutor in physics or math, in English or in Spanish, you know how to find me. You can find me at shorttakes331@gmail.com, or you can leave a comment in the comment section below. If anything is unclear, of course, feel free to do so, and I'll try to reply, or maybe I'll reply in a future video. That's all I have for you today, and until next time.